Okay, welcome back. Today we are talking about syntax analysis again, and we'll be dealing with derivations. Right, so before we get into parse trees and the things that come as a result of a parser, we need to deal with derivations, which are kind of the basis for all the work that a parser would do. And how do derivations work? We have the non-terminal deriving some strings containing either non-terminals or terminals, or an empty string. Given a grammar, E derives E plus E, or E star E, or minus E, or E in parentheses, or ID. We can say that E derives minus E. That's what this arrow means. Production has occurred and it's replacing the non-terminal E with a string of I, E, E. Okay, we can also have E deriving other things, multiple steps, such that say we have a string I minus into parenthesis id plus id. This is a string that can be derived in 0 or more steps. 0 steps is not possible, but you get the point. E derives minus E. We can start from this guy. We'll go further to say E derives minus into parenthesis E, and E can also derive minus parenthesis open E plus E, according to this production rule. Then we can have E deriving minus into parenthesis id plus E, and finally minus parenthesis id plus id, which checks out in 0 or more steps. So that's what we've got. So what just happened? We went from the non-terminal, which should have been the start symbol, but it kind of is a bunch of things. The start symbol derives something in the beginning. Let me change the color. Derives E. So this is what we've got. Then this still derives something else, and then something else, and then something else, and then something else. But essentially, they all come from this guy, this small little capital E. That's derivations. Okay, and we've got to talk about two things. There's something called the sentential form, and then something called a sentence. Sentential form and a sentence. What's a sentential form? A sentential form can be said to be uh, a string or a possibly empty string containing both non-terminals and terminals. Let me write that out. So let's just say we have S derives alpha in 0 more steps. Alpha here is a string of possibly empty string containing both terminals and non-terminals. So in this case, because it's containing non-terminals, it is not exactly the product of a language. It's incomplete. Basically, we can have it produce more things. So we can't exactly define that as the natural string of the language. It's not complete. But what is a sentence then? A sentence is a sentential form with no non-terminals. Basically, a sentence contains only terminals. That's the difference between the sentence and a sentential form. So a sentence is like a sentential form, but it doesn't have non-terminals. So this is a sentence. My id id plus id in parentheses. This is a sentence. There are no non-terminals here, so there's no possibility of any further breaking down, and because of that, this guy is a sentence. So a sentence contains only terminals, but a sentence can be said to be a sentential form without terminals. So the difference between a sentential form and a sentence is sentential forms contain non-terminals while sentences do not contain non-terminals. I believe that should be that. Yes, I've actually mentioned I've done some derivations, but then mostly, or we would not have a situation where we are just randomly deriving. Since we are dealing with parsers, we have to understand that parsers operate in. We have different types of parsers. We have the top-down parsers, and then we have the bottom-up parsers. I'm not going to describe them yet, but I'm just going to point out what they do and how they work. Top-down parsers use leftmost derivations, leftmost derivations, and bottom-up parsers use the rightmost derivations. How did we get there? Why are we talking about this? Is it important? Yes, it is. Why? Because these two guys are showing the behavior and how we actually derive stuff. We just don't land at a sentence. We actually have to derive the sentence from the start symbol of a grammar. And since there are so many possibilities, we do not want chaos. Language was never a thing of chaos. Language is structure. For everything that works, there's a system that makes it work. So if a language is understood by everybody, it is because there's a system that allows it to work. And in this case, we are having leftmost derivations helping top-down parsers and rightmost derivation helping bottom-up parsers, and they approach things in two different ways. The top-down parser would start from the root to the tree, to the leaves, pardon me, from the root to the leaves, while the bottom-up will start from the leaves to the root. So that's what we've got. I'll talk more on that later, but let's give ourselves some examples. So bringing back my favorite string id plus id, using that previous grammar, e derives e plus e times e, uh sorry, um, minus e into parentheses and id. So we have this guy. Let's say we are going to approach this from leftmost derivation. E derives, what do we start with? We start with the negative e because we are still preserving our non-terminal, but we have already produced a terminal on the correct part of this. Now, since it's leftmost, we are going to have to mark this guy out, and then we derive again. E derives minus, and then we use this production rule that says we are introducing a parenthesis. So we have that. Everything looks fine. I mean, this is leftmost derivation lm. I should add that. Remember, for the sake of identification, without you adding the lms or rms at the bottom of the arrow, you cannot exactly specify which you are doing. So bless me, we still have to go further with this non-terminal. If we were to impute an id now, we have terminated that and we didn't exactly produce the string that this language was supposed to generate. So what do? We go one step further with the leftmost derivation, and we have e plus e. This is where the difference between the rightmost and the leftmost become very, very clear. What is on the leftmost side? This guy is on the leftmost side, not this one. So we are going to have to take that one down first. No, we have to replace it first. Then leftmost derivation minus id, there's a parenthesis, then e, Now the only leftmost non-terminal is this guy, so we go further leftmost minus id plus id, and we have the string. But the behaviors are influenced by what kind of derivation they are. So e derives using rightmost derivation minus e. Furthermore, it derives minus parenthesis open e parenthesis close. E derives in rightmost derivation minus e plus e. It's me. Uh, Now again, it looks pretty simple because I mean it's just id plus id. What happens when we have a bunch of stuff going on like e times e, id times id plus id uh, times id again, and so on and so forth? When we have a long string, where we start from is important. How we derive is also important. So excuse me. Rightmost derivation one more time. We are going to start with what's on the right, which is this guy over here. So e id that, and then one more rightmost derivation id plus id, and then we have that. We see that it's not the exact same thing that just happened. uh, Structure and all that just helps us to know what to do, and these will be further more important when we get into actual parsing. So what next to note? Parse trees and derivations. It will do you well to keep in mind that a parse tree is just a graphical representation of a derivation. So let's say there's a derivation of a sentence minus parenthesis open id plus id. We just write that out, minus id plus id, with that same grammar. Why do I keep erasing it? Uh, Either this plus this, e times this, minus e parenthesis open or close, and id. Now a parse tree is going to be more like a graph. No, let's just call it a tree. It's basically a tree. So how does it work? Now to arrive at this, we went through that by deriving minus e, derived the minus parenthesis open or close that. We derived minus e plus e. Then we went on to do for, let's say, it doesn't really matter what the derivation mode is, but I'm just trying to get to the end of this. Okay, so what does the parse tree look like? You have this amazing looking e separating into the terminals and the non-terminals. So leaf the leaves are the outermost nodes, and they don't connect to anything anymore. They cannot be broken down any further. They don't derive anything. Now this is a non-terminal, and so because of that, the derivations still continue. So what does this derive? It can derive the open parenthesis, another non-terminal, and then close. But that's not all we want. We want it to go one step further. We make another production which is accurate. Then we go to the last terminals, which id. Note the terminals. We have that, we have that, we have id, we have the plus, we have id again, and we have this, and this gives us this. So the process can also be shown. I will clean this up. The process can be shown in steps. So for instance, e derives e, which will have minus, and then this. So what derivation? Let's say we are using the leftmost derivation. So this derives this, which also derives this. Okay, so what does that derive again? This derives minus e, open bracket that, and this can derive e plus e using this. Now let's say we are using the leftmost. So on the leftmost derivation, it's going to be this guy to be derived next. So that the derivation will occur with, so we have this, we have this, we have this, and then we go further to derive this, this, and this. So what now? Deriving ID from this E, and we have arrived at a terminal. So with leftmost derivation again, we can then complete our parse tree by doing this. And there we have it. Our parse tree is ready. Now, there is, of course, the same issue that we found in automata theory, which is ambiguity. Ambiguity can easily exist in this case as well. So let's talk about ambiguity. What is ambiguity exactly? If the parse tree generated by a string is, if more than one parse tree, can be generated by a string, then we say that that grammar is ambiguous. Okay. We have to give an example to prove what we are talking about. So let's say we have id plus id star id with that same set of productions and rules. um, First things first, let's go with yeah, I'll just write it out again. I don't want you guys guessing what is what. So E derives E plus E also derives E star E derives minus E derives the open parenthesis and close, E also derives ID. So we are not making any assumptions anyway. So let's say we start with the first production. We have E plus E. We are trying to get to this string over here, which is possible. So we derive that. Let's say we are using the leftmost derivation. Should we be using the leftmost derivation though? Yeah, let's just see what we can do. Let's say we are using the leftmost derivation. Now, because this is the leftmost and we do not really want that to do anything, we can just make that into ID right now. Then we have one more leftmost, which is the last non-terminal on this list. Then we further derive ID plus E times E. So from here we can go a step further with this. So E derives in another step ID plus ID times E. Then we can go one more step again. Leftmost derivation ID plus ID times ID, and that checks out. So how do we know something is ambiguous? We need to have more than one um, parse trees. So this already gives an, okay, we got something going on. What happens when we use another production to start? So let's say we use E star E to begin. Remember, it's leftmost, so we have this. It's actually easier at this point. We can just derive E plus E star E. What next? E, in leftmost derivation, we just derive ID plus E star E. E, leftmost derivation, ID plus ID star E. And finally, with leftmost derivation again, ID plus ID star ID. Notice something, we used two different productions to arrive at the same string. That can already give you a sense of foreboding that some weird stuff's going on, but we still need proof. So what do? I'm going to draw the parse trees for these guys. So what do we have? For the first guy, we can start with E plus E. What then do? We have an ID going on here, and then we derive E star E. and then we can have an ID going on there too. ID going on there. Terminal, 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 terminal. We have ID plus ID star ID. Checks out. So having that, oh, give me a sec. Then again, we can start with something else. E derives E star E, which in turn will derive E plus E. Then this guy on this other end would derive ID simply, and this goes further down to derive ID and ID. Terminal, 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 terminal. ID plus ID star ID. And this also passes the vibe check, and they are both the same. But these are two different parse trees. These are not the same, but they have the same results. So we can claim that this is ambiguous. How do you handle ambiguity? You might want to restructure the grammar. You make it such that the grammar is not as free. Usually the degree of freedom that the grammar gives can give room for ambiguity. Reminds me of Yoruba very well. There are some words that you say in Yoruba that are so ambiguous that parents use that thing to threaten children, and well, the outsiders might not pick up the signs that it's a threat, but the child knows exactly what his mom is saying. If his mom says, "Oh, you can go ahead," and you go ahead and eat what your mom says you should go ahead and eat, you might die. You actually might die. But yeah, let's not talk about our moms here. Yeah. Moving on. Moving on. Let's take an exercise. Let's take an exercise. So we have this grammar. We have S derives SS plus, which also derives SS star and derives A. Then they gave us a string to work with. They said A plus A star. That is our string. Now, what are the questions? Number one, we want you to give the leftmost derivation. Pardon my writing. Yeah, I mean, we want the rightmost derivation. Next, we want the parse tree of the string. Then finally, we want to know if it is ambiguous or not. So let's just do something. I'll make this smaller. I will. Looking at the question, we might already begin to see that this is a more well-structured language. Now, grammar. Okay, let's take a look at this. We have SS plus, SS star, and A, and we see the string we've been given. Now, let me just separate them: leftmost, rightmost. We have these two guys. So let's start with leftmost. S derives on leftmost derivation. Which of these do we pick first? Star or the plus? If you notice the structure of this string, you know that if you start with a plus, you've already failed the question, because the entire string doesn't end with a plus, and there's no non-terminal behind the plus to give us the answer we are looking for. So we definitely have to start with the star. So SS star is the production we have to go with. So what do we do from here? Since it's leftmost derivation, we know that we are starting from the leftmost side. And looking at the string again, we see that we can have an SS plus going on here. So we just introduce that. So we have SS plus S star, and we already have the shape for this language, for this string rather. So what do we have again with leftmost derivation? We make this the leftmost S into an S star. We go one more step again. Leftmost derivation AA plus S star. Then we go one more time again with leftmost derivation AA plus A star. Now for the rightmost derivation, if we start with that Rm, we also need to start with the SS star, because regardless of whether we are using leftmost or rightmost, the structure of the string remains the same. So we have SS star. What then do we do from here? We are working with the rightmost, so we do not actually want the rightmost to become another non-terminal. It's not necessary. What we will then do is we'll make the rightmost into a terminal. We make it at A, because we are having an A here. So now we are only left with the rightmost. The only terminal, non-terminal here is now the rightmost. So we move forward with the rightmost derivation again, and we can derive SS plus from the S and A star, and then we go from here rightmost derivation to fill in S. Rightmost is this S, so we have S A plus A star, and then finally from rightmost derivation we have A plus A star. Now the question I have is this okay? First of all, I'll generate the parse tree. Let me scale down on this. So to generate the parse tree, we take a look. What do we have going on? So S can derive S star, and then if we look at it from the leftmost derivation, what can we do again? We can make this derive A, this guy derive no, sorry, forgive me for that. We first have to do the other S plus, and then this guy remains the same, so we can have A going on there, A going on there, and also A right there. So terminal, 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 terminal. We have A plus A star, and then we've done that. Let's try and look at it from the rightmost derivation. How do we do that again? We have S derives SS star, and then we had this S derive A, but then we also had this S derive S plus, and then this derived A and A. Let's separate this guy from the mist. Sorry, this move you closer. Okay, so we see A, this. Even with though that the structure looked kind of different from the rightmost and the leftmost, but the tree is so identical. It's identical. There's no difference. The arrival looked different, but it's the same parse tree. So I don't see any new way of doing this tree. We can't start with the SS plus. We have to start with the SS star, and then it's still the same structure that it gives for a tree. So since we cannot generate more than one parse tree for this, we can say it is unambiguous. So there we have it. We've done the leftmost derivation, the rightmost derivation. We generated the parse tree. We checked if it is ambiguous or not. And since we couldn't make it ambiguous by creating more than one parse tree, we have to accept that it is unambiguous. So thanks for watching, and I'll see you guys in the next video. Thanks for watching.